And we are recording. Let me start the stopwatch too. Okay, now, right on this page, there is something else that is very important that we should talk about. And, I am going to now define, right on this diagram, I'm going to define the attenuation cross section, because that's also a very important thing. The attenuation cross section, and the symbol is sigma. Okay, now cross section implies that cross section is something which is a area. Okay, now here's how it comes in. So we're going to define that attenuation cross section sigma. The attenuation constant A is defined as, because you can see that how much am I going to attenuate? Well, that is proportional to the number density of scatterers, right? So this is the number density of scatterers. I'm sorry, this is getting small, but number density of scatterers, and then it's proportional to that. But then also, what is the cross section of each scatterer? Meaning, photons are coming and hitting these atoms, and well, I mean, what's the cross section of each scatterer? So this is a definition, all right? Now, what you notice here is that the number density, let me write this down here again. A is equal to n sigma. The A is, we just said, it is a 1 over centimeter, right, the dimension. And the number density will be a 1 over centimeter cube. And it could be meter also, 1 over meter cube. It's just that in all the examples we will talk about per centimeter cube, those are the dimensions that are used. And of course, then sigma is centimeters squared. Okay? So this is your attenuation cross section. Okay? And by the way, when I said number density of scatterers, it could be scatterers or absorbers. Yeah, written all over my diagram. Okay? So is this cool? So there's the attenuation cross section. There's the attenuation constant. Okay? That's the difference between the two, right here in this relation. Okay. Okay, so one more grammar thing that is left is, so we've discussed this, and there's one more grammar issue that we need to talk about, and that is the photon flux. Okay, so continuing with grammar, laser grammar. Now discuss photon flux. And the symbol used for photon flux is, sometimes people call this phi, sometimes phi. I never decide what, so whatever comes out of my mouth spontaneously, so phi, okay? But that might become a phi at any moment, and I wouldn't know. Okay, so this is of course related to the intensity, right? It's proportional to the intensity incident on sample. And so you see, I use the word incident here. So really what will matter is what is going to come up repeatedly when we write our rate equations is the incident photon flux. Okay, meaning that the sample is being illuminated by some light. Now that light may have been produced by initial spontaneous emission within the gain medium, or it might be from a pump laser that, like an argon ion laser that is trying to get the dye to laze. Okay, but somehow these photons are being created somewhere, maybe even within the sample, and then they're illuminating all the other atoms in the sample and trying to get the stimulated emission to take over. Okay, so all right, so now let me make this relation between the incident photon flux and the incident intensity a little more concrete. You see the intensity, if I divide the intensity of the light by the energy in a photon, h nu, okay, so what is this? I mean, it's just what I said right now. Intensity of the light divided by energy per photon. Okay, and this is actually what the flux is defined as. Okay, this incident photon flux. And let's just get an idea for the dimensions. The dimensions are important because, here also we introduced an attenuation constant. We wrote down its dimensions, and we noticed that the attenuation cross section is different from the attenuation constant in its dimensions. I mean, of course, the number will be different, but the dimensions are different. One is a per length, the other is a area. Okay, so dimensions are a very good way to tell apart different things. So this is the flux, and now what are the dimensions for the flux? So the intensity, of course, is, so if I continue with this guy here, intensity is, intensity is, like when you measure in the lab, it's a watts per meter squared or a milliwatts per centimeter squared, like that. So you can see from here, it's power per unit area. Power is energy per unit time, okay, and then per unit area. So that's your intensity, right? Power per unit area divided by the energy per photon, right? So this would be the energy and energy cancel, and we're left with the photon is in here, like I need to bring it up into the numerator, so it would become the number of photons, photons per unit time per unit area. Okay, and so that's what it's the number of photons per unit time per unit area. That's the flux, photon flux. Okay, and so so from this I can write, therefore, the number of photons that are absorbed or scattered. Okay, and actually, if we just focus on the, number of photons that are absorbed or scattered per unit time, well, that would be, so you take the incident flux, right? And if I, you notice that, this is number of photons absorbed or scattered per unit time. So what about this guy? So the area, I mean, if I multiply this by sigma, then you notice that I took the incident flux, I multiplied it by the attenuation cross section, right? So I multiplied it by an area. And so the dimensions then become number of photons now absorbed or scattered because I've multiplied it by sigma, right? And the area got taken out because I multiplied it by sigma on the right hand side, and so those are my dimensions. Okay, so I got this relation, and you notice that the dimensions now on either side, it's a 1/2, right? So this has dimensions of 1/2. This is a number per unit time, so it's a 1/2. Okay, so what what it is that this guy, the incident photon flux multiplied by the attenuation cross section, describes absorption. Okay, so in the context of the laser, the scattered goes away, right? It's more absorbed is what we focused on. And so this describes absorption from the ground state. Okay, so from the ground state to the excited state, and it describes two processes. It describes one, absorption from ground state to excited state, and it also describes stimulated emission back. From the excited state to the ground state. Both these processes are described by this term here. Okay, so how much of the incident flux actually got absorbed? And once you get absorbed, then, well, that incident flux is still there. And so the same interaction or the same absorption will also, not the same absorption, what I mean is that if you've absorbed and gone from the ground state to the excited state, then the same flux is still there. And if you multiply it by sigma, then it also describes the stimulated emission process back down to the ground state, because that's how many photons are. You know how stimulated emission occurs when there is another photon nearby to cause the stimulated emission. So absorption and stimulated emission are very much the same process, except one goes from ground state to excited state, the other goes from excited state to ground state. Okay. Any questions so far? Is this good? Is everyone okay with the incident photon flux and this term that we've just described? One way to get more comfortable is to actually look at how to apply these terms. And the simplest case, so let's apply these concepts. Apply concept of photon flux and attenuation cross section to the case of a two-level atom, to the simplest case, simplest light atom interaction a two-level atom. Okay, let's look at this case. And so then I think, and you will now, this is the part where Wolfgang Pauli said rate equations are very easy to write. Okay, this is what he was talking about. So now that we know the language, we will see that setting up the equations are very easy. So here's a two-level atom. There is level 1, let's call it 1, and level 2, okay? And now there is absorption and stimulated emission between them. So photons are being, stimulated emission makes you come down, absorption makes you go up. The rates are equal, and actually that's the reason you can't make a laser out of a two-level atom, but let's be quantitative about it. Let's say N1 and N2 are the population densities. Okay, so N1 and N2 are the population density. And you know, the equations that I'm setting up right now, this is exactly what laser engineers do. And almost this is all that laser engineers do from the theoretical standpoint. Okay, they do, of course, a lot of experimentation, but this is the theory. So N1 and N2 are the population densities in levels 1 and 2. Let's also include the spontaneous emission. Spontaneous, because in addition to the stimulated emission, you also have spontaneous emission. And let's call the spontaneous emission rate. Now, previously, when I was setting up the cartoon model, remember this? There was spontaneous emission, and I called the spontaneous emission rate F. And there was a gain thing here and all that. But the spontaneous emission rate, I called it F there, but a better term, something that all authors use, let's call it A to 1. 2-1 just means from 2 to 1. The A is actually something that Einstein used in his original derivations. He's the one who came up with some of these ideas, not for a laser. Even he could not imagine a laser, but when he was discussing stimulated emission, that's when he came up. So it's called Einstein's A coefficient. So he described spontaneous emission with an A coefficient, and he described stimulated emission with a Einstein's B coefficient. So, you know, that's how he did it. So this terminology has stuck. So I'm going to revert to that. All right. So there's your spontaneous emission rate. And now if I want to set up the rate equations, well, first of all, I note that N1 plus N2, now these are functions of time, right? Because you have population going out from one into the other and then back and all that kind of stuff. But the total is some constant, N, meaning that there are no energy levels that you get lost to. It's a closed system. Okay, and so that means that N1 dot plus N2 dot is 0, right? I just took the time derivative. So because, you know, in the end I'm interested in rate equations. Now, what is a rate equation? A rate equation just describes how the population in each level changes. And so if I'm looking at the population for level 1, right, I'm going to set up the rate equations and then we'll take a break. So what are the population, how is the population in level 1 affected? Well, what causes an increase in the population? Every time you have spontaneous emission, then the atom jumps to the ground state. That's an increase in the population of the ground state. So the spontaneous emission rate multiplied by the number of the atomic density, or the number of atoms per unit volume in level 2. Now, these are population densities. Sometimes it just helps to think of them as numbers. So what I'm trying to say is that the number of atoms in level 2 multiplied by the spontaneous emission rate gives me the number that moved into level 1. And it's a gain, hence the plus, right? So the rate multiplied by the number of atoms that were doing it will give me the number of atoms that jumped into the level 1, right? And these are actually population densities, but you see what I mean, okay? So there. But what causes a loss from 1? And so here's where we're going to use the photon flux idea. Stimulated emission, no, what I mean is absorption. Absorption causes a loss from 1 into 2. And what is the rate at which absorption occurs? It is simply the incident flux multiplied by the attenuation cross-section. So that's the rate at which, did we write that down here? It's the number of photons absorbed per unit time. So this is the rate, right? So the rate, there it is, and it's absorbed, but I have to, uh, how much of this is absorbed, it depends on how much there was in N1 to begin with. By the way, I didn't finish this term here. The spontaneous emission multiplied by the number of atoms in the excited state. That's what comes out from the excited state, falls into the ground state, and it's a gain. A loss is the absorption. So I should label these guys as I go. This is spontaneous emission from 2 to 1. This guy is absorption from 1 to 2, right? When you absorb, the atom gets taken from level 1 out to 2. But there is also stimulated emission, which is happening at exactly the same rate as the absorption. So finally, you have a sigma phi, and this is stimulated emission. Now that rate is the same, but how much of it is coming back down, it depends on how much is up there in N2. So that's where there's a difference between these terms, right? And so this is stimulated emission from 2 to 1. Does everyone see how this equation was set up? Is everyone okay with this? All in favor say aye.
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 Okay, so some ayes. All who are still thinking say uh-huh. Oh, okay, nice. And then all who object. If anyone objects to this holy equation, speak up at this time. But you don't have to remain silent forever. You can always bring it up later again if you like. So is everyone okay with this equation? Do you see how we sort of use those ideas to write out a rate equation? Dimensionally, everything looks good. Okay, the n's are all population densities, right? And the things that are multiplying them here are rates, so it all works out pretty well. Okay, and you don't need to evaluate n2 dot differently because you know that this is just minus n2 dot. Okay. So let me, and I see I'm like at a whopping 23 minutes, so I'm just going to do one more thing here. I'm just going to take this equation and write it like so, that I'm going to collect the n1 terms together and the n2. So I have a A21 n2, and it's a very simple equation. You have a sigma phi, right? And then you have n2 minus n1, and the reason I wanted to do this is this is a very important thing. That's your population inversion. This is very important because you need a population inversion for lasing action to happen. Okay, and I'm going to put a box around this. And then we can look at this, and let me do one last thing here because and then we'll go into our little break. We're going to define gain. This is so important. Define the gain G as exactly equal to this. It's the sigma times the population inversion. This is the actual, when we talk about the gain for a laser, this is what it is. And so you see that it has dimensions of, what does it have dimensions of? It has, this is centimeters squared, and the n's are density, right? So it's a 1 over centimeter cube. So this has a 1 over centimeter. So now, who else had units of 1 over centimeter? Do you recall? We just talked about it today. the attenuation constant. And so what we're going to find is that the attenuation constant and the gain are very closely related. A negative gain is attenuation, and a negative attenuation is a gain. Okay, we will formalize that relation in a moment, but let us now stop here, and let me stop the recording. Let's take a break, like a 2 or 3 minute break, more like question break, and then actually we're what, 3:20 right now. So then after this we'll come back for 10 more minutes to wrap up, and then we'll just stop right there. Okay, so I'm stopping the